Have you ever pushed your code to production only to watch it freeze, choke, and melt down under a tiny bit of traffic? You check the logs, you see thread dumps, and you have no idea why everything just stopped. The truth is, most thread pool related problems are silent killers. Today, we are going to tear apart Java's thread pool internals. We are going to cover every configuration knob, every hidden trap, and every advanced trick so that you can build systems that stay fast, stay alive, and never embarrass you in front of your users. Welcome back. Today, we are going to cover types of tasks and specific execution policy required for them, thread starvation deadlock, sizing your thread pools, queue strategies, saturation policies, and even how to extend ThreadPoolExecutor to add your own statistics. By the end, you won't just use thread pools, you will own it. Grab your favorite drink because this is going to be a long but incredible rewarding ride. The first big idea is something called implicit coupling. Your task and thread pool you run them on have a relationship. If you change the pool, you might break your tasks without even realizing it. Let's talk about dependent tasks first. These are the tasks that wait for the result or side effect of another task. In well-behaved world, tasks are independent. You can change pool size freely, but when tasks start depending on each other, you create hidden constraints. If you submit a task that waits for another task that's still in the queue, you're asking for trouble. Imagine you are building a report generator. One task retrieves user data and then it submits another task to format that data into PDF. If both tasks run in same fixed size thread pool and pool is full of retrieval tasks, none of the following tasks can start. The retrieved tasks are stuck waiting for formatting tasks that will never run. That is deadlock. Second, thread confined tasks. This is when your tasks rely on being executed by single thread. For example, if you have single threaded executor, you can safely use non-thread safe objects because you know only one thread accesses them at a time. But if you later switch to multi-threaded pool, suddenly those objects are shared across threads and you get data corruption. Third is response time sensitive tasks like GUI updates or API calls that need to return fast. If you mix long running tasks with short ones in a small pool, the short tasks get stuck behind the long ones and your users start typing impatiently. The lesson here is simple. Know your tasks. If they are not independent, document the execution policy they need. Otherwise, you are flying blind. Let's zoom in on one of the most painful problems, thread starvation deadlock. The main difference between classic deadlock and thread starvation deadlock is the resource being fought over. In normal deadlock, the resource is a lock. In thread starvation deadlock, the resource is the thread itself. Let's understand how this happens. So this happens when every thread in a pool is blocked waiting for a task that is still sitting in the work queue. Because no thread can pick up that waiting task, the system freezes. Let's understand with example. In a single threaded executor, if you submit a task that submits another task to the same executor and waits for it, you get instant deadlock. If first task is running, but the second task is in the task queue and the first task never finishes because it's waiting for second task to finish. So here we have single thread deadlock demo. We create new single threaded executor. So the main thread submits this outer task which logs this message, and after that it submits another inner task to the same executor. After that it waits for the result of the inner task. But this thread blocks forever here because inner task is stuck in the task queue. The single thread is already occupied by the outer task at this location. So the outer task never gets completed, so the program hangs there. And the main thread, which is at this location, gets blocked as well because since outer task is not finished, it will not get the result and the shutdown will never be reached. So let me run this program. Let's see what happens. So do you see? This is deadlock. The program hangs indefinitely. In the larger pools, the same thing can happen. If all the threads are blocked waiting for a task that are still queued. The classic example is a pool that processes web requests, where each request submits another task to the same pool and waits for the result. Under load, all threads can end up waiting and pool starves. So, how do you prevent this? First, be careful with dependent tasks. If you must have them, ensure your pool is large enough so that there is always a free thread to run the dependent task. Or better, use separate pools for different stages and always document any constraints in your code so that future you will thank you. Now, let's talk about long running tasks, the tasks that take forever. A thread pool can become clogged with long running tasks, increasing the service time even for short tasks. If your pool is too small relative to the number of long running tasks, eventually all threads will be busy doing slow work and your fast tasks will sit in the queue waiting. One technique to mitigate this is to use timed waits instead of unbounded waits. Most blocking methods in Java like thread.join, blockingQueue.put, or countdown latch.await have timed version. If the wait times out, you can mark the task as failed, abort it, or requeue it. This guarantees that each task eventually makes progress, freeing up threads for others. Also, if you constantly see your pool full of blocked tasks, that's the strong sign your pool is too small. So, how big should your pool be? This is not a guesswork. The ideal size depends on your tasks and your hardware. The golden formula is number of threads equal to the number of CPU cores multiplied by target CPU utilization multiplied by 1 plus the ratio of wait time to compute time. So, for compute intensive tasks like there is no waiting, the wait time to compute time ratio is nearly zero. So the formula roughly gives us n CPU plus 1. The plus 1 handles minor page faults. Even compute intensive threads occasionally take a page fault or a pause for some other reasons. So an extra runnable thread prevents CPU cycles from going unused when this happens. And for IO intensive tasks like database calls or file reads, wait time to compute time ratio can be large. Suppose you have a task that makes a database call. It takes 100 milliseconds to process the result, that is a compute time, but it waits 900 milliseconds for the database to respond. So your wait time to compute ratio is 9, and hence the total number of threads are 10 times of the number of cores. That's a huge difference. The formula isn't exact, it's the starting point. You should profile your application under load and adjust. And if you have different types of tasks with different behaviors, consider using multiple thread pools so each can be tuned separately. Now we get to the heart of it, the thread pool executor, the class. The executor's utility class gives you convenience, but the true control comes from instantiating thread pool executor directly. Its constructor has 7 parameters: core pool size, the number of threads to keep alive even if they are idle; maximum pool size, the maximum number of threads; keep alive time, how long idle threads beyond core size wait before being terminated; time unit, the work queue, the queue that holds the tasks; the thread factory, how threads are created; and reject handler, what to do when queue is full and the pool is at max size. So let's break down these parameters. Thread creation and teardown. The core pool size. is the target number of threads. Even when idle, pool tries to keep that many threads alive. Max pool size, that is the upper limit. The pool creates new threads only if the work queue is full and the current size is below the maximum. One common trap: developers sometimes set core pool size to 0, thinking threads will clean up. But if the work queue has any capacity, the tasks will just pile up in the queue, and pool will never create a thread until the queue fills. That's probably not what you want. You can use allow core thread timeout true so that even core threads can time out if they remain idle longer than keep alive time, solving this issue cleanly. Few more things to note. The new fixed thread pool factory sets core and max to the same size with an infinite keep alive time. So you must be thinking what value we put for keep alive time here to make it infinite. Maybe a few hundred years or what? No. New fixed thread pool uses keep alive time equal to 0, means non-core threads terminate immediately after finishing task. But in fixed thread pool, core threads are equal to maximum threads. All threads are considered core threads. By default, core threads never time out since allow core thread timeout is set to false. This effectively means threads are kept alive indefinitely regardless of keep alive time. Secondly, new cache thread pool sets core size to 0 and max size to integer dot max value and 1 minute of keep alive time. It grows as needed and shrinks when idle. But wait, didn't we just talk about the trap with core pool size equal to 0? That's a great observation. But behavior of new cache thread pool is quite different from fixed thread pool. Internally, it uses synchronous queue, which holds a task. Now it's time to talk about task queue. The work or task queue is critical. There are three basic approaches: unbounded queue, like linked blocking queue without capacity. This is used by new fixed thread pool. It's simple, but if tasks arrive faster than they can be processed, the queue grows without bound and can cause memory exhaustion. Bounded queue, like array blocking queue or bounded linked blocking queue. This limits how many tasks can wait. When the queue is full, the pool can create more threads up to the max pool size or use saturation policy. We'll talk about saturation policy shortly. Bounded queue helps prevent memory issues, but they require careful tuning of queue size and pool size together. And the third is synchronous handoff, uses synchronous queue. This isn't really a queue, it's a mechanism where each insert must wait for a take and vice versa. If no thread is ready to take, a pool will create a new thread if possible. New cache thread pool uses this. That's why even when core pool size is 0, tasks don't pile up in the queue. It's great for unbounded pools but can cause thread creation spikes. Also, note that if your tasks are dependent on each other, bounded queues can lead to thread starvation deadlock because inner task may never be enqueued. In those cases, you might need an unbounded configuration like new cached thread pool. Saturation policies. When the work queue in the thread pool is full and the pool is at max size, the saturation policy kicks in. ThreadPoolExecutor provides four built-in policies. These are the standard implementations of rejected execution handler, which you can pass as constructor argument while creating ThreadPoolExecutor. So let's see all these policies. First is abort policy, which is the default one. It throws rejected execution exception when queue is full and pool size is at max, and the caller must handle this exception. Discard policy, as name suggests, it silently discards the new task. Discard oldest policy discards the oldest task in the queue and then tries to submit the new task again. Note here, if you use a priority queue, this discards the highest priority element, probably not what you want. At last, we have CallerRunsPolicy. Instead of rejecting, it executes the task in the caller's thread. This acts as a throttle. The caller thread does the work, so it can't submit more tasks for a while, giving a pool a time to catch up. The caller run policy is especially powerful in web server. If the pool is overloaded, the main thread that accepts the connection will start processing the request itself. That means it can't accept new connections. So the requests start backing up in the TCP layer. The overload pushes outward and the system degrades gracefully instead of crashing. But what if you want the submitter to block instead of making it run the task until pool thread is available? There is no built-in policy for that, but you can implement it using Semaphore. You create Semaphore with the bound equal to the pool size plus the queue capacity. And before submitting, you acquire the Semaphore, and after task finish, you release it. This limits the number of pending tasks and naturally blocks the caller when the limit is reached. This is a great technique for controlling injection rates. Let's try to implement it. Bounded executor, which limits the number of tasks submitted to an executor by using semaphore. It blocks the caller when the limit is reached, providing backpressure. So we take executor and maximum number of tasks allowed to be pending. That means task may be running or queued. So here we have submit task method where we submit a task to the executor. If the limit of pending task has been reached, the calling thread blocks until a slot becomes available. So we first acquire a permit before submitting. Acquire method gets blocked if there is no permit available. Once permit is acquired, the task is submitted to the underlying executor. Inside the submitted task, after the actual work is done, the semaphore permit is released. If the underlying executor rejects the task, maybe because it has been shut down, we release the permit immediately to avoid leaking it. And then we throw that exception. So how to use it? So here I have a thread pool executor where core pool size and max pool size is set to 3. Keep alive time is 0 seconds and the worker queue is a bounded queue with capacity of 2. We use this executor and the bound, which is summation of pool size and queue capacity, and pass it to our bounded executor. Then we submit 10 tasks to this bounded executor one by one. Each task log the task ID, then sleep for 2 seconds. If it gets interrupted, we restore its status and then it's finished. And once all tasks are finished, we shut down the executor gracefully with the timeout of 30 seconds. The key benefits of this bounded executor is this provides natural back pressure. When the system is overloaded, new tasks are not dropped or thrown as exceptions. Instead, the caller, example a web server thread, blocks, naturally slowing down the request rate and allowing the system to recover. This is much more graceful degradation than throwing rejected execution exception. So let me run this. So we are submitting 10 tasks. We submit a task, submitted successfully, second, third, fourth, fifth, sixth. Oops, we got the rejected execution exception. But wait, we didn't shut down the executor. Then how come we got rejected exception? The program is not stopped yet. So let's debug. Let me stop this and create a debug pointer and run it in a debug mode. We got it. So the executor threw the rejected execution exception while submitting the task. If we check the logs, so we submitted first, second, third, fourth, and fifth task, and while submitting the sixth task, we got that error. So this is strange. We submitted the task 6. All 5 permits are acquired. How come 6th task got the permit? And if it got the permit, why did executor reject the 6th task if it has the permit? So here is the reason. When we submit tasks sequentially, the way we are doing here, the first 5 acquire permits and go through. On the 6th submission, we expect this acquire call to block. But in practice, one of the earlier tasks may finish quickly and release its permit. That allows the sixth task to acquire the permit, but the executor is still saturated. Three threads are busy and two tasks are queued. Queue is full and all threads are busy. So executor.execute method throws rejected execution exception. This mismatch happens because Semaphore tracks permits, which is external bound, but the executor tracks threads plus queue slots, which is internal bound. They are not perfectly synchronized. So a permit can be released while the queue is still full. So how to fix it? Instead of using bounded queue, we can switch to an unbounded linked blocking queue. That way, the executor never rejects the task. But to prevent runaway memory usage, we keep the semaphore as the true throttle. So the pattern becomes executor with unbounded queue, so there are no rejections, and semaphore with fixed permits. That's our chosen bound depending upon the requirements. This ensures no rejected execution exceptions when we submit the task and no unbounded memory growth, because at most the count of tasks in queue will never be more than number of permits. So let's rerun it by changing worker queue to unbounded link blocking queue, and let's observe the queue size even when we submit, let's say, 100 tasks. Also, let me set the pool size equal to the available CPU cores. So here you can see we have successfully completed the execution and the shutdown. So here we have pool size of 16. That means we have 16 threads and bound is 18. That means at max 18 tasks will be in pending state, either in running or queued. Since our bound or queue capacity is 2. So if we check the queue size, so here I see 1. If I go down, so I see at max 4, 5. Here I can see. So you noticed here the queue size is not more than the bound, which is 18. So will not get memory issues. And that's how you create a bounded executor which blocks the submitter thread and creates a natural backpressure. Every time a thread pool needs a new thread, it uses thread factory. The default factory creates a simple non-daemon threads with generic names, but you can provide your own factory to give your threads meaningful names like db worker 1 instead of pool 1 thread 1. Custom uncaught exception handler to lock uncaught exceptions. Daemon status if you want threads not to prevent JVM shutdown, and even custom thread subclasses that add logging or other behavior. Here is an example my app thread that keeps track of how many threads are created and alive and logs when threads start and exit. This is invaluable for debugging and monitoring. So this thread subclass, my app thread, tracks total created threads and currently alive threads using atomic integer static counters. Provides debug lifecycle flag that when true logs thread creation and exit log using Java util logging. This also sets default uncaught exception handler that logs any uncaught exception with severity severe. The thread name includes the pool name, maybe myworker-1, for easy identification in the logs and thread dump. The custom thread factory, my app thread factory, it implements new thread method and returns new my app thread with specific pool name. This factory can be passed to any thread pool executor constructor. Let's see how. So we create thread pool executor with custom thread factory. Tasks are submitted, and when the pool needs a new thread, they are created by this factory. The logging output shows when threads are created and exit. Since we set debug lifecycle to true, we can see that, making it easy to monitor pool behavior. The static methods get created and get alive provide insight into thread usage at any point. This pattern is invaluable for debugging, performance monitoring, and ensuring that uncaught exceptions in pool threads are properly handled instead of being silently lost. So let me run this and show you how the logging looks like. So initially 3 threads are created, 3 were alive. We can see the task and the threads running it, and at last we can see how many threads are alive and how many were created. One of the great things about ThreadPoolExecutor is that most of its configurations can be changed after it's built using setters like set core pool size, set maximum pool size, set keep alive time, set thread factory, set rejected execution handler. This is perfect for dynamic tuning or for building self-adjusting pools. But be careful if you create an executor via executors.new single thread executor. You get an unconfigurable wrapper. If you try to cast it to ThreadPoolExecutor and try to change its size, you can't do it. It's wrapped by unconfigurable executor service. This is a good thing because a single threaded executor promises that task will never run concurrently. Changing the sides would break that promise. You can also use executors dot unconfigurable executor service to wrap your own executors, preventing anyone from modifying the policy after the fact. Threadpool Executor was designed to be extended. It provides three hooks. First is before execute. It's called before a task runs in the worker thread. After execute hook, it is called after the task finishes, whether normally or by exception. Note here, if the task completes with an error, this hook is not called. And the last is terminated hook. It is called after all tasks have finished and all worker threads have shut down during executor shutdown phase. These hooks let you add logging, timing, monitoring, or statistics without cluttering your task code. Let's look at a real example of timing thread pool, a custom executor which measures execution time of every task and logs average execution time when it shuts down. It uses thread local to store start time. In before execute hook, it records system.nanotime into that thread local instance. In after execute hook, it retrieves the start time and computes the duration and updates two atomic counters, one for total tasks and one for total time. And finally, in terminated hook, it calculates and logs the average time. This is a fantastic way to get performance metrics without changing a single line of your task logic. You can extend this idea to track thread utilization, log rejected tasks, or even send metrics to a monitoring system. This is the kind of power you get when you go beyond simple executors and truly master thread pool executor. Wow, we covered a lot today, from implicit couplings and starvation deadlocks to sizing formulas, queues, saturation policies, thread factories, and even custom extensions. If you made it this far, you now know more about thread pools than most professional developers. That's all for this video. I'll see you in the next one with a new problem. Until then, keep your threads in check and your pools well tuned. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.